So if we wish to discuss charging a capacitor, that process follows fairly similarly to the process of discharging a capacitor. So if we're talking about a situation where we want to charge up a capacitor, first of all, our circuit does have to change a little bit. We have to include a source of potential in the circuit. We've got to put in a battery. We begin with the switch open, so no current flow at all at the beginning. And we also begin, if we're trying to charge up the capacitor, then it means at the very beginning there's no charge on the capacitor. And no current flow, of course, because the switch is open. So our circuit then has a source of potential. It's got a switch which closes at t equals 0. And then we've got a resistor and a capacitor. When the switch closes, we do get a current flow because now we have a complete connected circuit. So we get a current flow I. That current flow is the flow of charge, and the charge eventually ends up starting to charge the capacitor plates. So at t equals 0, we close the switch, and the charge flows. At some general time t, the capacitor has an amount of charge which we'll call Q. And the circuit is going to have an amount of current I. We remember there is a relationship between current and charge. So current is change in charge over change in time. The charge on the capacitor plates is increasing, so our current is equal to plus dq over dt. Okay, and that plus sign comes in because the charge on the capacitor plates are increasing. If we want to solve this problem, we apply Kirchhoff's potential law. So we draw a loop, and we write our potential law for that closed loop. That says that the net potential around the loop, that's going to be our potential increase due to the battery, our drop across the resistor, and our drop across the capacitor. So we lose potential going across the capacitor because we're adding charge to it. The top plate becomes positive and the bottom plate becomes negative. So as we go around that circuit, we go from positive to negative, a drop in potential. And that has to equal 0. So from this equation, what we have to do is, like we did for the charging capacitor, we have to rearrange it and solve. The only thing that's really very different here would be the limits of the integral. When we were discharging the capacitor, we started with an amount of charge QO and we went to our general charge Q. For this situation, we start with a charge 0 and we go to charge Q, so slightly different limits. Our time integral will still go from 0 to t. When we do this solution, what we get for our answer is that the charge on the capacitor at some general time t is the potential epsilon times the capacitance C times 1 minus e to the minus t over RC. Again, we're going to be using our time constant tau is equal to RC. And we're also going to notice that we have epsilon times C, the potential times the capacitance. That's the maximum charge. In terms of our previous problem, that would have been Q0. So our maximum charge is, we might call it Q maximum for this problem, or Q0 to keep with the notation of the previous problem. So for our charging capacitor, charge Q is Q naught 1 minus e to the minus t over tau. We might also solve for our current. We know that current is the change in charge over the change in time. That's our maximum current times e to the minus t over tau. So there's a summary. You're welcome to work through that math and reach out to me if you have any questions. A couple of interesting things here. Our charge starts at 0 and it increases to some value. It never actually gets there because it's an exponential, but it approaches that maximum value. You might notice that as your charge gets bigger and bigger, it doesn't change as much anymore. That means that the current goes to 0, and that matches what our equation tells us. If our time t starts to get big, then our whole expression here is going to go to 0. And that kind of makes sense. As your capacitor plates get really charged up, once it's holding the maximum amount of charge, the charge can't flow anymore. We can't get any more charge on the plates. That means the charge stops flowing and there's no more current flowing in the circuit. That idea is going to come back a couple of times over as we do more problems. So once your capacitor is fully charged, the current stops flowing. This example now is a little bit of a recap of what we've just done. So we have a circuit connected to a battery with a resistor and a capacitor. We close the switch at time t equals 0 and the capacitor begins to charge. Part A, what's the potential across the capacitor a very long time after the switch has closed? So long time means something. Long time means that the capacitor is fully charged. If the capacitor is fully charged, then the capacitor acts like an open circuit. No more charge can move around. If it's an open circuit, then the current is 0. If the current is 0, then the potential drop across the resistor, current times resistance, is equal to 0, which tells us that the potential across the capacitor must have the same magnitude as the potential of the battery. So the potential across the capacitor is the same as the potential across the battery after a very long time. Okay, what is the maximum charge, so the maximum amount of charge on the plates, in terms of the potential of the battery, the resistance of the resistor, and the capacitance? So let's see about that guy. So we know that capacitance is charge over potential. That tells us that our charge is our capacitance times our potential. So our maximum charge is our capacitance, that's a constant, that doesn't change, times the maximum possible potential across the capacitor. That happens when it's fully charged, and that potential is equal to epsilon. So B builds on part A. So part C, we did discuss in the last little bit. In this circuit, is I equal to positive dq by dt or negative dq by dt? Well, we already discussed that I is equal to plus dq by dt. And that's because we know that in general, I is dq by dt, a little bit of charge that's moving through our circuit. dq, if we want to think about that in terms of what's happening to the capacitor, so we're increasing the amount of charge. So we have a charge Q on our capacitor plate. When we increase that charge by a little bit, that's when we get a current flow. That's because the charge on the capacitor is increasing. So that's where that plus sign comes from. I know that tends to get a little bit tricky for people. Part D, find an expression for the current as a function of time and graph the current as a function of time. Let's move on to the next slide to do that part. So we know our expression for our charge. Q is our maximum charge times 1 minus e to the minus t over tau. And we know that current is the change in charge over the change in time, or the derivative in charge with respect to time. So then our current I is d by dt of Q. Our Q max can come outside. We've got d by dt of 1 minus e to the minus t over tau. Let's see what we can do here. So the derivative of 1 minus e to the minus t over tau, the derivative of 1 is just 0 because 1 is a constant. The derivative of e to the minus t over tau is e to the minus t over tau times the derivative of minus t over tau, which is minus 1 over tau. Okay, a little bit complicated. The last thing we might notice is that our maximum charge, we found that in part B, that was equal to C times epsilon. Let's try and pull those things together there. So our current I is our maximum charge, capacitance times the potential of the battery, times the derivative of 1 minus e to the minus t over tau. That's equal to minus times a minus gives us a positive 1 over tau, which is 1 over RC, times e to the minus t over tau. Okay, if you look at this expression, you might notice a C on top and a C on the bottom, and then you might notice you have potential over resistance. So epsilon over R is equal to the maximum current. That happens at t equals 0. So you might also call that I of 0. So for our very last step, we'll write down I equals I0, or I maximum, doesn't matter, e to the minus t over tau. Then if you wanted to make a plot of that, it starts at the maximum value. So our graph will have I on our vertical and time on our horizontal. It starts at the maximum value of I0, and it falls off exponentially, kind of like this. What else we might point out here? At t equals 5 tau, our current is equal to 0.0001 times I0. Oh, I put too many zeros in there, I think. Yeah, too many zeros. Sometimes it's hard to count off all those zeros. So at t approximately equal to 5 tau, that's when the current stops flowing and our capacitor is fully charged.